Welcome back, everybody. In this tutorial, you are going to code a deep deterministic policy gradient agent to beat the continuous lunar lander environment in Pytorch. No prior experience needed. You don't need to know anything about deep reinforcement learning. You just have to follow along. Let's get started. So we start, as usual, with our imports. We'll need OS to handle file operations and all of the stuff from Torch that we've come to expect, as well as NumPy. I'm not going to do a full overview of the paper. That will be in a future video where I will show you how to go from the paper to an actual implementation of deep deterministic policy gradients. So make sure you subscribe so you don't miss that. But in this video, we're just going to get the very high-level overview, the 50,000 foot view, if you will. That will be sufficient to get an agent to beat the continuous lunar lander environment, so that's good enough. So the gist of this is we're going to need several different classes. So we'll need a class to encourage exploration, in other words, a type of noise. And you might have guessed that from the word deterministic. It means that the policy is deterministic, as in it chooses some action with certainty. And so if it is purely deterministic, it can't really explore, so we'll need a class to handle that. We'll also need a class to handle the replay memory, because deep deterministic policy gradients works by combining the magic of actor-critic methods with the magic of deep Q-learning, which of course has a replay buffer. And we'll also need classes for our critic and our actor, as well as the agent. So that's kind of a mouthful. We'll handle them one bit at a time, and we will start with the noise. So this class is called OU Action Noise, and the OU stands for Ornstein Uhlenbeck. So that is a type of noise from physics that models the motion of a brownian particle, meaning a particle subject to a random walk based on interactions with other nearby particles. It gives you a temporally correlated, meaning correlated in time, set type of noise that centers around a mean of 0. So we're going to have a number of parameters, a mu, a sigma, a theta. If I could type, that would be fantastic, as well as a dt, as in the differential with respect to time, and an initial value that will get an original value of none. So if you want to know more about it, then just go ahead and check out the Wikipedia article, but the overview I gave you is sufficient for this tutorial. So, of course, we want to save all of our values. X0, and we want to call a reset function. So the reset function will reset the temporal correlation, which you may want to do that from time to time. Turns out it's not necessary for our particular implementation, but it is a good function to have nonetheless. So next, we're going to override the call function. If you aren't familiar with this, this allows you to say noise equals OU action noise, and then call noise. So that allows you to, instead of saying noise.getNoise, just say noise with parentheses or whatever the name of the object is. So that's overriding the call function. So we'll have an equation for that: x previous plus theta times the quantity mu minus self.x previous times self.dt plus self.sigma times numpy square root of self dt times mp random normal size equals mu shape. So it's a type of random normal noise that is correlated in time through this mu minus x previous term. And every time you calculate a new value, you want to set the old value, the previous value, to the new one, and go ahead and return the value. So the reset function, all that does is check to make sure x0 exists. If it doesn't, it sets it equal to some 0 value. So x previous equals self.x naught if is not none, else numpy zeros like in the shape of self.mu. That's it for the action noise. Again, this will be used in our actor class to add in some exploration noise to the action selection. Next, we need the replay buffer class, and this is pretty straightforward. It's just going to be a set of numpy arrays in the shape of the action space, the observation space, and rewards, so that way we can have a memory of events that have happened so we can sample them during the learning step. if you haven't seen my videos on Deep Q Learning, please check those out. They will make all of this much more clear, as well as checking out the videos on actor critic methods, because this, again, DDPG kind of combines actor critic with Deep Q Learning, so that will really be helpful for you. I'll go ahead and link those here as well, so that way you can get edumacated. So scroll down a bit. We want to save our mem size as max size. So the mem counter will start out at 0. Again, this is just going to be a set of arrays that keep track, or matrices in this case, that keep track of the state, reward, action transitions. And that will be in shape mem size, so however number of memories we want to store, and input shape. So if you are relatively new to Python, this star variable idiom, it isn't a pointer if you're coming from C or C++. It is an idiom that means to unpack a tuple. So this makes our class extensible, so we can pass in a list of a single element, as in the case of the lunar lander and continuous lunar lander environment that we'll use today, or later on when we get to the continuous car racing environment, we'll have images from the screen. So this will accommodate both types of observation vectors. It's a way of making stuff extensible. And the new state memory is, of course, the same shape, so we just copy it. It looks like I am missing a parenthesis somewhere. I guess we'll find it when I go ahead and run the program. So, oh, it's not self.init, it's def. There we go. Def init. Perfect. So we'll also need an action memory. And that, of course, will also be an array of zeros in the shape of mem size by number of actions. I believe that means I need an extra parenthesis there. Yes. And we'll also have a reward memory. And that will just be in shape mem size. We also need a terminal memory. So in reinforcement learning, we have the concept of the terminal state. So when the episode is over, the agent enters the terminal state from which it receives no future rewards. So the value of that terminal state is identically 0. And so the way we're going to keep track of when we transition into terminal states is by saving the done flags from the OpenAI Gym environment. And that'll be shape numpy zeros, mem size, and I've called this float 32. It's probably because Torch is a little bit particular with data types, so we have to be cognizant of that. We need a function to store transitions, which is just a state, action, reward, new state, and done flag. So the index is going to be the first available position. So mem counter just keeps track of the last memory you stored. It's just an integer quantity from 0 up to mem size. And so when mem counter becomes greater than mem size, it just wraps around from 0. So when they're equal at 0, and when it's equal to mem size plus 1, it becomes 1, and so on and so forth. So state memory subindex equals state, action memory index, reward equals state underscore, and the terminal memory, good grief, terminal memory index doesn't equal done, but it equals 1 minus done. So the reason is that when we get to the update equation, the Bellman equation for our learning function, you'll see we want to multiply by whether or not the episode is over, and that is facilitated by 1 minus the quantity done. Just increment mem counter. And next we need to sample that buffer. So sample buffer, and that will take in a batch size as input. So the max memory is going to be the minimum of either mem counter or mem size. Not the max, but the minimum. Then batch is just going to be a random choice of maximum index of max mem, number of elements, equal to batch size. Scroll down a bit. And then we want to get a hold of the respective states, actions, rewards, and new states, and terminal flags, and pass them back to the learning function. Sub batch new states, rewards, you know, it's not easy to type and talk at the same time, apparently. And let's get actions, self.action memory match, and terminal. Good grief. So we want to return states, actions, rewards, new states, and the terminal flags. Perfect. So that is it for our replay memory. So you're going to see this a lot in the other videos on deep deterministic policy gradients because we're going to need it for basically anything that uses a memory. Next, let's go ahead and get to the meat of the problem with our Critic Network. And as is often the case when you're dealing with Pytorch, you want to derive your neural network classes from nn.module. That gives you access to important stuff like the train and eval function, which will set us in train or evaluation mode. Very important later. I couldn't get it to work until I figured that out. So a little tidbit for you. You'll also need access to the parameters for updating the weights of the neural network. So let's define our initialize function. The beta is our learning rate. We'll need input dims, number of dimensions for the first fully connected layer, as well as second connected layer, number of actions, a name. The name is important for saving the network. You'll see that we have many different networks, so we'll want to keep track of which one is which. Very important. As well as a checkpoint directory for saving the model. Also very important because this model runs very, very slowly, so you'll want to save it periodically. And you want to call the superconstructor for Critic Network, and that will call the constructor for nn.module, I believe. Input dims equals input dims, fc1 dims. So these will just be the parameters for our deep neural network that approximates the value function. The number of actions, a checkpoint file, and that is os path join checkpoint dir with name plus underscore DDPG. And if you check my GitHub repo, I will upload the train model because this model takes a long time to train. So I want you to be able to take advantage of the fully trained model that I've spent the resources and time training up, so you may as well benefit from that. So next up, we need to define the first layer of our neural network, just a linear layer, and that'll take input dims and output fc1 dims. We're also going to need a number for initializing the weights and biases of that layer of the neural network. And we're going to call that f1, and it's divided by 1 over the square root of the number of dimensions into the network. So self.fc1.weight.data.size, and that returns a tuple, so I need the 0th element of that. And then we want to initialize that layer by using t torch nn init.uniform underscore the tensor you want to initialize, which is fc1 weight data up from -1 to positive f1. So this will be a small number of order 0.1 or so, not exactly 0.1, but of order 0.1. And you also want to initialize the biases, bias.data, and that gets the same number. And again, in the future video when we go over the derivation of the paper, I'll explain all of this, but just for now, know that this is to constrain the initial weights of the network to a very narrow region of parameter space to help you get better convergence. Perfect. So, oh, and make sure to subscribe so you don't miss that video, because it's going to be lit. So BN1 is a layer norm and takes FC1 dims as input. The batch normalization helps with convergence of your model. You don't get good convergence if you don't have it, so leave it in. So FC2 is a second layer, another linear. It takes FC1 dims as input and outputs FC2 dims. Good grief. And we want to do the same thing with initialization. So it's 1 over the square root of self.fc2 weight data dot size 0, and you want to do tnn init uniform underscore fc2 weight data minus f2 up to f2. Make sure that's right so we don't screw that up because that's important. That looks correct. The syntax here is the first parameter is the tensor you want to initialize, and then the lower and upper boundaries. So next we need bn2, which is our second batch norm layer. fc2 dims. And just a note, the fact that we have a normalization layer, a batch norm type layer, means that we have to use the eval and train functions later. Kind of a nuisance. It took me a while to figure that out. The Critic Network is also going to get a action value because the action value function takes in the states and actions as input, but we're going to add it in at the very end of the network. Linear actions, C2 dims, and this gets a constant initialization of 003. Or sorry, the the next one, the output gets a initialization of 003, and since this is a scalar value, it just has one output. And you want to initialize it again uniformly. .q.weight.data, and that gets minus f3 up to f3. And likewise for bias data. Okay, so now we have our optimizer, and that will be the atom optimizer. And what are we going to optimize? The parameters, and the learning rate will be beta. So you notice that we did not define parameters right here, right? We're just calling it, and this comes from the inheritance from nn.module. That's why we do that, so we get access to the network parameters. Next, you certainly want to run this on a GPU because it is an incredibly expensive algorithm, so you want to call the device. So t.device, CUDA 0 if t.CUDA.is available, else CUDA 1. So I have 2 GPUs. If you only have a single GPU, it will be else CPU. But I don't recommend running this on a CPU. So next, you want to send the whole network to your device by self.to self.device. We are almost there for the critic class. Next thing we have to worry about is the forward function, and that takes a state and an action as input. Keep in mind the actions are continuous, so it's a vector, in this case length 2 for the continuous lunar lander environment. It's 2 real numbers in a list or NumPy array format. So state value, so FC1 state, and then you want to pass it through BN1 state value, and finally you want to activate it. f.relu state value. Now, it is an open debate whether or not you want to do the relu before or after the batch normalization. In my mind, it makes more sense to do the batch normalization first, because when you are calculating batch statistics, if you apply the relu first, then you're lopping off everything below 0, right? So that means that your statistics are going to be skewed toward the positive end, when perhaps the real distribution has a mean of 0 instead of a positive mean, or maybe it even has a negative mean, which you wouldn't see if you used the relu function before the batch normalization. So just something to keep in mind. You can play around with it. Feel free to clone this and see what you get. But that's how I've done it. I did try both ways, and this seemed to work the best. So next we want to feed it into the second fully connected layer. BN2 state value, and then we want to BN2 that. Oh, sorry, I already did that. One second, let me let the cat out. So we've already done the batch normalization. We don't want to activate it yet. What we want to do first is take into account the action value. And what we're going to do is activate the action through the action value layer and perform a ReLU activation on it right away. We're not going to calculate batch statistics on this, so we don't need to worry about that. But what we want to do is add the two values together. So state action value, f.ReLU, t.add, state value, and action value. Other thing that's a little bit wonky here, and I invite you to clone this and play with yourself, is that I am double ReLUing the action value function, so the action value quantity. So I do a ReLU here, and then I do a ReLU on the add. Now, this is a little bit sketchy. I've played around with it, and this is the way it works for me. So if you can clone it and get it to work a different way, the other possibility is that you don't do this ReLU here, but you do the ReLU after the add. So ReLU is a non-commutative function with add. So what that means is that if you do an addition first and then a ReLU, that's different than doing the sum of the two ReLUs, right? So if you take ReLU of -10 plus ReLU of 5, you get a ReLU of -10 is 0 plus ReLU of 5 is 5, so you get 5. If you take the ReLU of -10 plus 5, then you get ReLU of -5 or 0. So it's a non-commutative function, so it does matter the order, but this is the way I found it to work. I've seen other implementations that do it differently. Feel free to clone this and do your own thing with it. I welcome any additions, improvements, or comments. So then we want to get the actual state action value by passing that additive quantity through our final layer of the network. And go ahead and return that. A little bit of bookkeeping. We have a save checkpoint function, and you'll say print, and then you want to call t.save self.stateDict. What this does is it creates a state dictionary where the keys are the names of the parameters and the values are the parameters themselves. And where do you want to save that? You want to save that in the checkpoint file. Then you also have the load checkpoint, good grief, checkpoint function, and that does the same thing, just in reverse. Loading checkpoint, and you want self.load state dict t.load self.checkpoint file. So that is it for our Critic network. Now we move on to the actor network. And that, of course, derives from nn.module. We have an init function, takes alpha, if we could spell correctly, input dims, fc1 dims, fc2 dims. This is pretty similar to the Critic network. It will just have a different structure. In particular, we don't have the actions. I can't type and talk at the same time, but it's pretty similar nonetheless. So input dims we want to save, and actions, fc1 dims, fc2 dims, same deal. Let me go copy the checkpoint file function just to make life easy. Perfect. I like to make life easy. So we have our first fully connected layer, and in.linear takes self.input dims as input and fc1 dims. And of course that operates in the same way as I discussed in the replay buffer, where it will just unpack the tuple. Next we have the initialization value, very similar, 1 over mp square root self.fc1.weight data size 0th element, and we want to initialize the first layer uniformly within that interval. Init uniform underscore fc1 weight data minus f1 and f1. Copy that. That will be fc1 bias data. fc2 is another linear layer. It takes fc1 dims as input and outputs fc2 dims, as you might expect. And the initialization for that will be basically the same thing except for layer 2. So fc2 weight data, and then, you know what, let's just copy this paste and make sure we don't mess it up. FC2, F2, ooh, good grief, and plus minus F2, and that is all well and good. Other thing we forgot is the batch norm, and that is NN layer norm, and that takes FC1 dims as input. Likewise for layer 2, that is another layer norm, takes FC2 dims as input shape, and that doesn't get initialized, but we do have the F3, and that is 003. This comes from the paper. We'll go over this in a future video, but don't worry about it. Self.mu, mu is the representation of the policy in this case. It is a real vector of shape and actions. It's the actual action, not the probability, right? Because this is deterministic. So it's just a linear layer. Takes FC2 dims as input and outputs the number of actions. And we want to do the same thing where we initialize the weights. Let's copy, paste, and instead of FC2, it will be mu. And instead of F2, it is F3, as you might expect. Am I forgetting anything? I don't believe so. So finally, we have an optimizer, and that's again optim.addem self.parameters, and learning rate equals alpha. We also want to do the same thing with the device. T.device CUDA 0 if t.cuda.is available, else CPU, and finally send it to the device. That is that. So next we have the feed forward. So that takes the state as input. So I'm just going to call it X. This is bad naming. Don't ever do this. Self.fc1. Do as I say, not as I do. Self.bn1 of state. Value of X. That's a mistake. It should be X. X equals self.fc2 of X. bn2 X. And then X equal t.tan hyperbolic self.mu of X, and then return X. So what this will do is pass the current state or whatever state or set of states, batch in this case, you want to look at, perform the first feed forward pass, batch norm it, value, send it through the second layer and batch norm, but not activate, send it through to the final layer. No, I take that back. I do want to activate that. Silly me, f.value x, and then it will pass it through the final layer mu and perform a tangent hyperbolic activation. So what that will do is it'll bound it between -1 and +1, and that's important for many environments. Later on we can multiply it by the actual action bounds. So some environments have a max action of +or -2. So if you're bounding it by +or -1, that's not going to be very effective. So you just have a multiplicative factor later on. And then I'm going to go copy the two save and load checkpoint functions because those are precisely the same. That's it for our actor. Next, we come to our final class, the meat of the problem, the agent. And that just gets derived from the base object. And that gets a whole bunch of parameters, alpha and beta. Of course, you need to pass in the learning rates for the actor and critic networks. Input dims, a quantity called tau. I haven't introduced that yet, but we'll get to it in a few minutes. We're going to pass in the environment. That's to get the action space that I talked about just a second ago. The gamma, which is the agent's discount factor. So if you're not familiar with reinforcement learning, an agent values a reward now more than it values a reward in the future, because there's uncertainty around future rewards, so it makes no sense to value it as much as a current reward. So what's the discount factor? You know, how much less does it value a future reward? 1%. That's where we get a gamma of 0.99. It's a hyperparameter. You can play around with it. Values like 0.95 all the way up to 0.99 are typical. Number of actions, we'll default it to 2. A lot of environments only have 2 actions. The max size of our memory, that gets 1,000,000, 1, 1 through 3, 1 through 3. Layer 1 size equals default of 400. Layer 2 size 300 is our default. And again, that comes from the paper, and a batch size for our batch, learning from our replay memory. So you want to go ahead and save the parameters, equal tau, and you want to instantiate a memory. That's a replay buffer of size, max size, input dims and actions. We also want to store the batch size for our learning function. We want to instantiate our first actor. Yes, there are more than one. And that gets alpha, input dims, layer 1 size, layer 2 size, and actions equals n actions, name equals actor. So let's copy that. So next we have our target actor. So much like the DeepQ network algorithm, this uses target networks as well as the base network. So it's an off-policy method. And the difference here is this going to be called target actor. It'll be otherwise identical. This will allow us to have multiple different agents with similar names. And you'll see how that plays into it momentarily. We also need a critic. That's a critic network. Takes beta, input dims, layer 1 size, layer 2 size, and actions equals n actions, name equals critic. So let's be nice and tidy there. And we also have a target critic as well. And that is otherwise identical. It just gets a different name. And this is very similar to Q learning, where you have Q eval and Q next, or Q target, whatever you want to call it. Same concept. Okay, so those are all of our networks. What else do we need? We need noise. And that's our OU action noise. And the mu is just going to be numpy zeros of shape and actions. So it'll give you an array of zeros. This is the mean of the rewards over time. And next we need another function you may be able to predict if you've seen my videos on Q learning, which you should check out, is the update network parameters. And we'll call it with an initial value of tau equals 1. So what this does is it solves a problem of a moving target. So in Q learning, if you use one network to calculate both the action as well as the value of that action, then you're really chasing a moving target because you're updating that estimate every turn, right? So you end up using the same parameter for both, and it can lead to divergence. So the solution to that is to use a target network that learns the values of the states and action combinations, and then the other network is what learns the policy. And then, of course, periodically you have to overwrite the target network's parameters with the evaluation network parameters. And this function will do precisely that, except that we have 4 networks instead of 2. So next, we want to choose an action. And that takes whatever the current observation of the environment is. Now, very, very important, you have to put the actor into evaluation mode. Now, this doesn't perform an evaluation step. This just tells Pytorch that you don't want to calculate statistics for the batch normalization. And this is very critical. If you don't do this, the agent will not learn. And it doesn't do what you think the name implies it would do, right? The complementary function is train. It doesn't perform a training step. It puts it in training mode, where it does store those statistics in the graph for the batch normalization. If you don't do batch norm, then you don't need to do this. But if you do, what's the other function? Dropout. Dropout does the same thing, or has the same tick, where you have to call the eval and train functions. So let's start by putting our observation into a tensor. D-type equals t.float to self.actor.device. So that'll turn it into a CUDA float tensor. Now you want to get the actual action from the actor network. So feed that forward to self.actor.device, and this makes sure that you send it to the device, so it's a CUDA tensor. So mu prime is going to be mu plus t.tensor. What are we going to use? Self.noise. That'll give us our exploration noise. And that is going to be d type of float. And we will send that to actor device. And then you want to say, should be actor.train, shouldn't it? Yes, self.actor.train. Yes. And then you want to return mu prime cpu.detach.numpy. So this is an idiom within Pytorch where you have to basically do this, otherwise it doesn't give you the actual numpy value, right? It's going to try to pass out a tensor, which doesn't work because you can't pass a tensor into the OpenAI gym. So kind of a funny little quirk, but it is necessary. So now we need a function to store state transitions. And this is just kind of an interface for our replay memory class. So memory.store transition state action reward new state done. Simple. So now we come to the meat of the problem where we actually do the learning. So you don't want to learn if you haven't filled up at least batch size of your memory buffer. So self.memory.mem counter is less than self.batch size. Then you just want to return. Otherwise, action reward new state done. You want to sample your memory. Memory.sample buffer self.batch size. Then you want to go ahead and turn all of those into tensors. That's because they come back as numpy arrays. In this case, we'll put them on the Critic device. As long as they're on the same device, it doesn't matter. I do this for consistency because these values will be used in the Critic Network. So the dones equal t.tensor done to self-critic device. You need the new state t.tensor new state d type t float to self-critic device. You also need the actions critic.device, and you need states t.tensor device. And now we come to another quirk of Pytorch where we're going to have to send everything to eval mode. For the targets, it may not be that important. I did it for consistency. So we want to calculate the target actions much like you do in the Bellman equation for Q-learning, deep Q-learning. Target actor dot forward new state. We want the critic value underscore, which is the new states. So the target critic dot forward, and that takes target actions as input. So what we're doing is getting the target actions from the target actor network. In other words, what actions should it take based on the target actor's estimates, and then plugging that into the state value function for the target critic network. You also want the critic value, which is self.critic.forward for state and action. So in other words, what is your estimate of the values of the states and actions we actually encountered in our subset of the replay buffer? So now we have to calculate the targets that we're going to move towards for j in range self.batch size, and I use a loop instead of a vectorized implementation because the vectorized implementation is a little bit tricky. If you don't do it properly, you can end up with something of shape batch size by batch size, which won't flag an error, but it definitely gives you the wrong answer and you don't get learning. So target.append reward sub j plus self.gamma times critic value underscore sub j times done sub j. So this is where I was talking about the done flags. If the episode is over, then the value of the resulting state is multiplied by 0, and so you don't take it into account. You only take into account the reward from the current state, precisely as one would want. So now let's go ahead and turn that target into a tensor. Tensor target.to self-critic.device, and we want to reshape this. Target equals target.view self.batch size and 1. Now we can come to the calculation of the loss functions. So we want to set the critic back into training mode because we have already performed the evaluation. Now we want to actually calculate the values for batch normalization. .train self.critic.optimizer.0grad. In Pytorch, whenever you calculate the loss function, you want to zero your gradients. That's so that gradients from previous steps don't accumulate and interfere with the calculation. It can slow stuff down. You don't want that. So critic loss is just, good grief, f.mse means square error loss between the target and the critic value. So then you want to back propagate that backward and step your optimizer. Boom. So that's it for the critic. So now we want to set the critic into evaluation mode for the calculation of the loss for our actor network. So self.actor.optimizer.0grad. And I apologize if this is confusing. It was confusing to me. It took me a while to figure it out. This is one of the ways in which TensorFlow is superior to Pytorch. You don't have this quirk. I tend to like TensorFlow a little bit better, but you know, whatever. We'll just figure it out, man, and get it going. So mu equals the forward propagation of the state. You want to put the actor into training mode, and you want to calculate your actor loss. And that's just minus self.critic.forward state and mu. Actor loss equals t.mean of actor loss. Again, stay tuned for the derivation from the paper. This is all outlined there. Otherwise, it seems mysterious, but this video is already 45 minutes long, so you know that'll have to wait for a future video. Actor loss backward and self.actor.optimizer.step. And then we're done learning. So now after you've finished learning, you want to update the network parameters for your target actor and target critic networks. So self.update network parameters. Whew, man. Okay, so we're almost there, I promise. Let's go ahead and do that. Def update network parameters self and tau equals none by default. So tau is a parameter that allows the update of the target network to gradually approach the evaluation networks. And this is important for a nice slow convergence. You don't want to take too large of steps in between updates. So tau is a small number, much less than 1. So if tau is none, then you want to say tau equals self.tau. Now this may seem mysterious. The reason I'm doing this is because at the very beginning, when we call the initializer, we say update network parameters tau equals 1. This is because in the very beginning we want to update, we want all the networks to start with the same weights. And so we call it with a tau of 1, and in that case tau is not none, so tau is just 1, and you will get the update rule here in a second. So this is more hocus pocus with Pytorch actor.named parameters. So what this will do is it'll get all of the names of the parameters from these networks. And we want to do the same thing for target actor. Parameters, target, critic, params. Okay, now that we have the parameters, let's turn them into a dictionary. That makes iterating them much easier because this is actually a generator. So I believe, don't quote me on that. Critic params. The actor state dict equals dict of the actor params. Target critic state. Let's just do target critic dict equals dict params params. Boom. Okay. Almost there. So now we want to iterate over these dictionaries and copy parameters. So for name in critic state dict, critic state dict subname equals tau times critic state dict name dot clone plus 1 minus tau times target critic dict name dot clone. So the target critic dot load state dict critic state dict. So what this does is it iterates over this dictionary, looks at the key in the dictionary, and updates the values from this particular network. And you can see that when tau is 1, you get 1 minus 1 is 0, so it's just this equals tau 1 times that. So it's the identity, and then it loads the target critic with that parameter. So at the very beginning, it'll load it with the parameters from the initial Critic Network, and likewise for the actor network. So let's go ahead and copy this and just go ahead and change critic to actor, and then we'll be done with that function, and we'll only have one other thing to take care of before we get to the main program. Target actor state dict. I believe that is it. Yes, indeed it is. Now there should be target actor. Yes. Perfect. Okay, now it's right. So next up we have two other bookkeeping functions to save the models. So def save models. And you definitely want this because this thing takes forever to train. And self.critic and target actor and target critic. And load models does the inverse operation. And let's just copy all this. Load. Keep things simple, right? And again, I will upload, since this takes so long, I'm going to upload my saved model parameters to the GitHub for you. But this is it. This is 275 lines. So this is probably the longest project we have worked on here at Machine Learning with Phil. If you've made it this far, congratulations. We're already 50 minutes in, and we're almost done, I promise. So let's come over to our main function, and we want to import our agent. So DDPG torch import agent. We want to import Jim. We want to, yes, we want NumPy. We want my super duper awesome import plot learning function. And that is it. So env jim.make lunar lander continuous v2 agent equals agent alpha 0.123425, so 2.5 by 10 to the minus 5. Beta equals 0.00025, so 2.5 by 10 to the minus 4. Input dims equals a list with element 8. Tau 0.001. env equals env. Oh, that reminds me, I did multiply by the action space high in the function for the choose action. Don't worry, that'll be in the TensorFlow implementation, or I can leave it as an exercise to the reader. It doesn't matter for this environment. When we get to other ones where it does matter, I'll be a little bit more diligent about that. Batch size is 64, size 400, layer 2 size 300, and actions equals 2. Now, another interesting tidbit is that we have to set the random seed. This is not something I've done before, but this is a highly sensitive learning method. So if you read the original paper, they do averages over 5 runs. And that's because every run is a little bit different. And I suspect that's why they had to initialize the weights and biases within such a narrow range, right? You don't want to go all the way from plus and minus 1 when you can constrain it to something much more narrow. It gives you a little bit more repeatability. So we have to set the numpy random seed to some value instead of none. So in this case, I've used 0. I've seen other values used. Please clone this and see what happens if you input other seed values. So next we need a score history to keep track of the scores over time. And we need to iterate over 1,000 games. Done equals false. Score equals 0. Observation equals env.reset. That'll get a new observation. So while not done, agent.choose action obs new state reward done info equals env.step act agent.remember. We want to keep track of that transition. Obs act reward new state int done. Agent.learn. We learn on every step because this is a temporal difference learning method instead of a Monte Carlo type method where we would learn at the end of every episode. Keep track of the score and set your old state to the new state. So at the end of the episode, at the end of every episode, we want to print the place marker. So we'll say score history dot append score print episode I score %.2f score 100 game average %.2f. And what this will do is take the last 100 games and compute the mean, so that way you can get an idea of its learning. Remember, with the Lunar Lander environment, solved means that it has gotten an average score of 200 over the last 100 games. So every 25 games, we want to save the model, agent.save models, and at the end, file name equals Lunar Lander PNG. That's not in the loop. You want to do at the end of all the games. Plot learning, file name, no, score history, file name, and a window of 100 games. Wow, so an hour in, we finally finished this. Now we get to go to the terminal and see how many typos I made. I'm sure there's probably 50, so let's get to it. All right, so here we are. Let's see what we get. We want to run torch, Lunar Lander, fingers crossed. Okay, so that's a stupid one. So in line 30, we forgot an equal sign. Let's go back there and fix that. All right, here we are. So it says line 30. Yes, right here. All right. Did we do that again anywhere else? Not that I can see. But that's no guarantee. All right, so let's go back to the terminal. All right, let's try it again. Line 119. Okay. Typical. All right, so 119. Right there. So that's in the actor. Let's just scroll down. That's the agent class. I don't think I did it there. All right, I'm going back to the terminal. All right, so I started it and it ran, so let's see. built-in function has no function or method has no attribute numpy. All right, that's an interesting bug. Let's fix that. So that is on line 192 in our choose action function. And mu prime. Oh, that's why. It detaches a function, not an object. That should fix it. Let's head back to the terminal. Rewards is not defined. So that is in line 55. Okay. It's just called reward. There we go. Add the S and back to the terminal. Perfect. That's easy to fix. Mictor temp / DDPG. It's because I didn't make the directory first. That's easy. Perfect. Now it's running. So I'm not going to let this run all 1,000 games because it takes about a couple hours or so. Instead, let's take a look here. So I was running this earlier when I was making the videos for the recording the agent's play while making for this video, and you can see that within under 650 games it went ahead and solved it. So when you print out the trailing average for the last 100 games, we get a reward of well over 200. Now keep in mind, one interesting thing is that this is still actually in training mode. It's not in full evaluation mode because we still have some noise, right? If you wanted to do a pure evaluation of the agent, you would set the noise to 0. We'll do that in a set of future videos. There's a whole bunch of stuff I can do on this topic, but just keep in mind that this is an agent that is still taking some random actions. The noise is non-zero, and so it is still taking suboptimal actions and getting a score of 260 and still beating the environment even though that noise is present. And you can see it in like episode 626 where it gets a score of 26. So and then in episode 624 where it does 8.58 points. So that is pretty cool stuff. So this is a very powerful algorithm, and keep in mind this was a continuous action space, totally intractable for Q-learning, right? That is simply not possible. It's an infinitude of actions, so you need something like DDPG to handle this, and it handles it quite well. In future videos, we're going to get to the walker, the bipedal walker. We're going to get to the learning from pixels, where we do the continuous racing environment, and we'll probably get into other stuff from the Robo School of the OpenAI Gym. So make sure to subscribe so that you can see that in future videos. Go ahead and check out the GitHub for this so you can get the weight, so you can play around with this, so you don't have to spend a couple hours training it on your GPU. Make sure to leave a like, share this if you found it helpful. That is incredibly helpful to me. And leave a comment down below. I answer all my questions. I look forward to seeing you all in the next video.